Hello everyone, welcome back to our lecture on computer programming for engineering application. So previously we've talked about arrays, which are type of group variable in C. Think of arrays as a containers that hold multiple pieces of data, and the most common type of array we've discussed is the one-dimensional array. So it's like a single row of boxes where each box can hold something. And right now we're managing arrays by using subscripting. So subscripting is just a fancy way of saying that we're accessing individual elements inside the array. So it's like pointing to a specific box in our row of boxes to see what's inside. And we've also learned that arrays can be set up using something called designated initializers. This means we can specify the initial values for our array elements right when we create the array. So it's like filling our boxes with stuff as soon as we get them. And lastly, we mentioned that arrays can have more than one dimension. So imagine stacking multiple rows of boxes on top of each other to create a grid of boxes. And each row represents one dimension, and together they form a multi-dimensional array. So to sum it up, arrays are like organized storage units for our data, and we've been learning how to work with them using subscripting, designated initializers, and understanding that they can have more than one dimension. And now for today's lecture, we're going to talk about functions. So today our goal is to understand why learning about functions in C is important and what we hope to achieve by the end of the session. So firstly, we aim to enable you to write programs that are more modular, and modularity means breaking down our programs into smaller, manageable parts. So functions help us achieve this by allowing us to focus on specific tasks within our program, making our code easier to understand and maintain. And secondly, we want you to be able to write programs that are iterative and contain functions. So iterative programs are those that repeat a process until a certain condition is met. So by incorporating functions into our iterative programs, we can organize our code better and make it more efficient. And thirdly, we aim to teach you how to write programs that reuse code. So reusing code means that once we've written a function to perform a certain task, we can use that same function multiple times in different parts of our program. And this saves us time and effort and reduces the chances of errors creeping into our code. And next, we'll explore how to write recursive functions. And recursive functions are functions that call themselves. So they're especially useful for solving problems that can be broken down into smaller, similar subproblems. So understanding recursions opens up a whole new realm of problem-solving possibilities in programming. And lastly, we'll delve into writing programs that are called with arguments referred to as by value. And passing arguments by value means that the value of the arguments is copied into the function parameters. And this concept is fundamental to understanding how data is passed between functions in C. Let's begin by introducing what a function is in programming. So think of a function as a set of instructions that have been bundled together and given a name. So it's like a mini program within our larger program. And each function has its own set of declarations, like defining variables and statements, which is the actual instructions or actions. And this allows us to organize our code more efficiently and make it easier to manage. Now, let's talk about the advantages of using functions in our program. So, firstly, breaking down our program into smaller functions make it much easier to understand and modify. So instead of dealing with a massive block of code, we can focus on one function at a time, making our code more readable and maintainable. And secondly, functions helps us avoid duplicating code that's used more than once. So imagine if we had the same block of code repeated multiple times throughout our program. It not only makes our code longer but also increases the chances of errors slipping in. And by putting that code into a function, we can call it whenever we need it and eliminating redundancy and improving the efficiency of our program. And lastly, functions promote code reuse. So a function that we write for one program can be easily reused in other programs. And this saves us time and effort because we don't have to reinvent the wheel every time we encounter a similar task. And in programming, defining a function means creating a set of instructions that perform a specific task and giving it a name. So it's like writing a recipe for a particular dish and giving it a title so you can easily refer to it. Now, let's take a look at these simple programs to get a better understanding how functions work in practice. So by examining these following examples, we'll start to grasp the concept before we delve into the technical details. And we'll see how functions are defined, what parameters they may take, and how they are called to execute their task. And understanding these basic concepts will lay a strong foundation for us to explore more complex aspects of functions in C programming. So let's take a closer look at these programs and see how functions play a crucial role in organizing our code and making it more efficient. So first, let's delve into our first program example, which demonstrates how to compute averages using a function called average_n. And in this program, we aim to calculate the average of multiple double values stored in an array. And the function average_n is defined in the slide with the text colored orange. Now, let's break down this function. So, the function returns a value of type double, indicating that the average computed will be a double precision floating point number. And it takes two parameters, which is the array A, which is an array of double values, and n, which represents the number of elements in the array. And inside the function, we initialize a variable sum to store the sum of all elements in the array. We then loop through each element of the array, adding its value to the sum variable. And finally, we return the average value by dividing the sum by the total number of elements in the array n. And when calling this function, we provide the array of values and the number of elements as arguments. And the function then calculates the average based on these inputs and returns the result. So in programming, every function consists of two main parts. The first is the declaration and the second is the body. So the body of a function contains the actual executable code and is enclosed within braces. So for our average_n function, the body consists of 3 lines of code. And these lines perform the essential task of summing up all the elements in the array and calculating the average. So once the function executes the last statement in its body, it returns to the place in the program which it was called. So this means that the function hands back a value to the calling part of the program. So in the case of average_n, the value returned is the result of the calculation sum over n, which represents the average of the values in the array. And in programming, we want to use a function to perform a specific task. We make a function call. So a function call consists of the function name followed by a list of arguments enclosed in parentheses. So for instance, in our example, the average_n parentheses x and m is a call to the average_n functions. So here x and m are the arguments provided to the function. Arguments are pieces of information that we supply to a function to help it perform its task. So they can be variables, constants, or expressions of a compatible type. So when a function is called, the values of the arguments are copied into the parameters defined in the function declaration. So in the case of average_n parentheses xm, the values of x and m were copied into the parameters a and n of the average_n functions respectively. So it's essential to note that arguments don't necessarily have to be variables. They can be an expression of a compatible type. So expressions like average and A9 or average and X3 are perfectly legal function calls. And in our program example, once we call the average and functions and calculate the average, we typically want to use the result somewhere in our program. And to do this, we place the function called average and in the part of our program where we need to use the return value. So in other words, we integrate the function call directly into our code where the average value is required. So for instance, let's say we want to print the average of values stored in the array X using M as the number of elements. And we can achieve this by using the printf statement like this, like the one in the slide. Here, average and xm computes the average using the values in the array X and M. And then the printf statement prints the result to the console. And it's important to note that in this example, the return value of the average and function is not saved or stored anywhere, and the program is simply prints it and then discards it. However, if we needed to use the return value later in our program, we could capture it in a variable. We can achieve this by looking at the code in red at the bottom of this slide. Here, AFG or average is a variable where we store the return value of the average and functions, allowing us to use it later in our program if needed. So in our program example titled average.c, we have a program that reads 3 numbers from the user and uses the average and functions to compute their averages one pair at a time. Now, let's take a closer look at how the program works. First, the program prompts the user to enter 3 numbers. In our example, the user inputs the number 3.5, 8.6, and 10.1. And next, the program calculates the average of the numbers entered using the average functions. And for numbers provided, the average computed by the program is 7.4. Now, let's break down the code and understand how it works. So, let's start with the average and functions. So, this function takes an array of double values and integer n as parameters. And inside the function, it calculates the sum of all elements in the array using a for loop. And then, it returns the average value by dividing the sum by the total number of elements in the array, or n. And moving on to the main function, then the program declares an array X of size 3 to store the input numbers. And the program prompts the user to enter 3 numbers using printf and reads the input using scanf. It then calls the average and functions with the array X and the number 3 as a arguments to compute the average. And finally, the program will print the calculated average using printf. Now let's try to run this program. So here we can see the program will print the average value from our inputted number, which are 3.5, 8.6, and 10.1. And next, in this example, we'll explore a program that prints a countdown message. Let's focus on understanding how functions with no return value are declared and used. So here in this slide, we have a code snippet colored in orange. And in the snippet, we define a function named printCount. And it takes an integer parameter n, which represents the countdown number. And the function body consists of a single line of code that prints a message to the console using printf. And the message includes the countdown number provided as an argument. Now, let's discuss the return type of this function. We specify void as the return type, which indicates that the function does not return any value. And void is a special type in C that represents the absence of a value. So it is used when a function does not need to return anything back to the calling part of the program. And now to call the print count function, it must appear in a statement by itself, like the one in the slide. Here, print count is the name of the function, and I is the argument provided to the function. And the statement tells the program to execute the print count function with the value of I as its parameter. Now, let's discuss the countdown.c program, which calls the print count function 10 times inside a loop. So, in this program, a loop is used to repeat the calling of print count 10 times, and each time the loop iterates, the print count function is called with a different countdown number as its argument. So by calling print count inside a loop, we can efficiently print the countdown message multiple times without duplicating the code. And this demonstrates how functions can be called within loops to perform repetitive tasks efficiently. And it showcased the power of functions in organizing code and making it more readable and maintainable. Now let's dissect the code of our program example to print a countdown. So let's go through each part of the code and understand its functionality. So first, the start input output.header file is included, which contains declaration for input and output functions such as the printf. And then we define the print count function. This function takes an integer parameter n and representing the countdown number and prints a message to the console using printf. And moving on to the main function, so the program declares an integer variable I, and it uses a for loop to iterate from 10 down to 1. And in each iteration, it calls the print count function with the current value of I. So after the loop finishes, the main function returns 0, indicating a successful program execution. Now let's see the output of this program. So here we can see that the program counts down the number from 10 and terminated when it reaches 0. So in this example, we'll explore a program that prints a pun. We'll focus on understanding functions with no parameters and how they're declared and used. Let's take a look at the function printPun. Here we define a function named printPun. Notice that it has void in parentheses after the function's name. This indicates that the function does not take any parameters. And the function body consists of two printf statements, and the statements print the pun message to the console. Now, let's discuss the significance of void in this context. So, when a function has no parameters, void is placed in the parentheses after the function's name to indicate that it doesn't expect any input. So in this case, the void serves as a placeholder to denote the absence of parameters. So in summary, this example demonstrates how to define and use a function with no parameters. Such functions are useful for performing tasks that don't require any external input. So understanding how to work with functions without parameters expands our toolkit for writing modular and reusable code. So in this example, we'll continue our exploration of functions by focusing on calling a function with no arguments and understanding its usage within a program. So to call a function with no arguments, we simply write the function's name followed by parentheses like the arranged code on this slide. And it's important to note that even if a function doesn't take any arguments, the parentheses must still be present because they indicate that we're calling a function. Now, let's discuss the pun2.c program, which has the printPun function. And now we'll dissect the code of our program example to print a pun. Let's go through each part of the code and understand its functionality. So first, the standard input-output header file is included, which contains declarations for input and output functions such as printf. And then we define the printpon function. So this function takes no parameters, as indicated by void in the parentheses, and prints two lines of text to the console using printf. And moving on to the main function, in the main function we simply call the printpon function, and since printpon doesn't require any arguments, we call it with empty parentheses. And after calling the printpon, the main function returns 0, indicating successful program execution. And now let's see what will be printed after we run this program. So here we can see when the function doesn't have any parameter and return value, it will execute all the syntax inside the function. So in this case, the code print the pon from our code. Here in this slide, we can see the general form of a function definition. Here, the return type specifies the type of value that the function will return after execution, and it can be any valid C data types such as integer, double, void, and etc. So if the function doesn't return any value, void is used. And next, the function name is the identifier used to name the function, and it should be descriptive and reflect the purpose of the function. And parameters here in our function are optional and represent the input values that the function expects. And parameters are enclosed in parentheses and separated by commas. So if the function doesn't require any parameters, the parentheses remain empty. And declarations are optional and include variable declarations needed within the function. And declarations typically come at the beginning of the function body. And lastly, we have these statements, which are the actual instructions or actions that the functions perform. So statements come after the declarations and define the behavior of the function. Okay, so the return type of a function specifies the type of value that the function will return after its execution. And we also have rules governing the return type of the functions. First, unlike other data types, functions cannot directly return arrays in C. However, they can return pointers to arrays or other data structures that contain arrays. And next, when a function does not return any value, we specify its return type as void. And this indicates that the functions perform a task or action but does not produce a result. And in C89, if the return type is omitted, the function is presumed to return a value of type integer. However, it's considered good practice to explicitly specify the return type for clarity and readability. But however, in C99, which is the newer version of the C programming language, omitting the return type of a function is illegal, and all functions must have an explicitly declared return type. So in programming, there are various styles for formatting function definitions. So one common practice as a matter of style is to place the return type on a separate line above the function name. So in this slide, the return type double is placed on a separate line above the function name average. And this style is particularly useful when the return type is lengthy, such as unsigned long integer. And by placing the return type on a separate line, the code becomes more readable and easier to understand. And it helps to clearly identify the return type of the function before delving into its implementation details. And this formatting style is a matter of preference and varies among programmers and coding standards. However, it's essential to maintain consistency within a code base to enhance readability and maintainability code. And next, after we specify the return type of a function, we define its parameters. So after function's name, we provide a list of parameters enclosed within parentheses, and each parameter in the list is preceded by a specification of its data type. And parameters are separated by commas. So in our previous function definition to calculate average, double A and double N are the parameters, and they're both of type double, indicating that the function expects to double type values as input. And if a function does not require any parameters, we specify void between the parentheses to indicate an empty parameter list. So in C programming, the body of a function encompasses both declarations and statements. Now let's explore an alternative version of the average function to understand this concept. So in the function definition we have in this slide, we have both declarations and statements within the function body. So for the declaration inside the function body, we declare a variable sum of type double, and this declaration allocates memory for the variable but does not assign it any value. And then we have statements that perform operations. So in this case, we calculate the sum of A and B and assign it to the variable sum. And finally, we return the average of A and B by dividing the sum by 2. And next, variable declared within the body of a function have a limited scope and cannot be accessed or modified by other functions. Now let's delve into the rules regarding variable declarations within function bodies. So first, variables declared within the body of a function are local to that functions, and they exist only within the function's execution's context and cannot be accessed or modified by other functions in the program. And this helps in encapsulating data and prevents unintended modifications. In C89 standard, variable declarations must come first before all statements in the body of a function. This means that all variables must be declared at the beginning of the functions before any executable statements. However, in contrast, the C99 standard allows for a more flexible approach, and variable declarations and statements can be mixed within the function body as long as each variable is declared prior to the first statement that uses the variable. This will provide more freedom in organizing the code within the function. And next, the body of a function whose return type is void, also known as a void functions, can be empty. In the example we have in this slide, we have a function named primpun with a return type of void. However, the body of the function is empty, containing no declarations or statements, and leaving the body of a void function empty may make sense as a temporary step during program development. So it serves as a placeholder for where the future functionality or code logic will be added. So for example, if we intend to implement the functionality of printing a pun message within the printPun function later in the development process, we can start by defining the function within an empty body, and this allows us to focus on other aspects of the program first and come back to implement the function's functionality when ready. And using an empty function body in this manner helps in structuring the code and serves as a reminder for pending tasks or future enhancement. However, it's essential to ensure that any void function within an empty body is eventually implemented to fulfill its intended purpose in the program. And next, we're going to talk about function calls. So in programming, a function call is the act of invoking or executing a function. So a function call consists of the function name followed by a list of arguments enclosed in parentheses. So for example, in this example we have in this slide, average, print count, and printPun are function names, and x, n, and I are the arguments passed to these functions. And it's crucial to remember that if the parentheses are missing, the function will not be called. For instance, the code in the bottom of the slide is technically legal in C but has no effect. Without the parentheses, printPun is treated as a function pointer rather than a function call. So as a result, the function will not be executed. And ensuring that the function name is followed by parentheses with the appropriate arguments is essential for successfully calling functions and executing their functionality. And next, when calling a void function, which is a function that does not return a value, the function call must always be followed by a semicolon to turn it into a statement. For example, we have our orange colored code snippet here in this slide. In these examples, print count and print pun are calls to void functions. The semicolon at the end of each line indicates the end of the function call statement. On the other hand, when calling a non-void function, which is a function that returns a value, the return value can be utilized in various ways. For instance, you can see the red colored codes here in this slide. In these examples, average xn is a call to a non-void function, and the return value of the function call can be stored in a variable avg or average used in conditional statement if, or directly printed or utilized in other expression. So when calling a non-void function, the value returned by the function can be discarded if it's not needed for further processing. So in this example, average xn is a call to a non-void function. However, the return value of the function call is not assigned to any variable or used in any expressions. So instead, it is simply discarded. And this type of call is an example of an expression statement. An expression statement is a statement that evaluates an expression but then discards the result. And in this case, the function call is evaluated, but the return value is not stored or utilized further in the program. And while discarding the return value of a non-void function may be valid in some scenarios, it's essential to ensure that this behavior aligns with the intended functionality of the program. So in most cases, the return value of a function contains valuable information that should be utilized in some way within the program logic. So while it's generally odd to ignore the return value of a function, there are scenarios where discarding the return value makes sense. So for example, the printf function in C returns the number of characters that it prints. And consider our first code here in this slide. And this example, printf prints the string "Hi Mom" to console and returns the number of characters printed, including the new line character, and this value is then assigned to the variable numchars. However, in many cases, we might not be interested in the return value of printf. So instead, we simply want to display the message on the console without storing or utilizing the return value. In such scenarios, we can discard the return value of printf. And now, in the statement at the bottom of our slide, printf is called to print the message "Hi Mom" to the console, but the return value indicating number of characters printed is ignored. While it's essential to consider the return value of functions and utilize it appropriately in most cases, there are exceptions where discarding the return value aligns with the intended behavior of the program. And when intentionally discarding the return value of a function, C provides a mechanism to make this intention explicit and clear. Now let's take a look at the code snippet we have here in the slide. So in this example, void is placed before a call to printf, and the syntax explicitly indicates to the other programmers that the return value of printf is being deliberately discarded. And using a void in this manner serves as a visual cue to communicate the programmer's intention. And it signifies that the return value is intentionally ignored rather than being overlooked or forgotten. And while discarding the return value of a function is sometimes necessary for a certain programming task, it's essential to ensure clarity and maintainability in the code. So by using void, programmers can make their code more readable and understandable for others who may review or work with the code in the future. Okay, next, here in the prime.c program, we aim to determine whether a given number is prime. Here when executed, the program prompts the user to enter a number, and in this example, the user enters the number 34, And the program then utilizes a function named s prime to determine whether the entered number is prime or not, and this function returns true if its parameter is a prime number and false if it is not. And inside the s prime function, the program divides its parameter n by each of the numbers between 2 and the square root of n. And if the remainder of the division is ever 0, it indicates that n is not prime. And by employing this approach, the program systematically checks for factors of the entered number, allowing it to accurately determine whether the number is prime or composite. Now let's break down the code from our previous slide to understand how it works. So let's first analyze the key components of the code. First, we include the header file start boolean to use the boolean type for representing boolean values, and start input output for start input or output operations. And next, the isPrime function takes an integer n as input and returns true if n is a prime number and false otherwise. And here inside the isPrime function, we first check if n is less than or equal to 1. If so, we immediately return false, as numbers less than or equal to 1 are not prime. And we then loop through potential divisors, starting from 2 up to the square root of n. And for each divisor, if n is divisible by the divisor without a remainder, we return false, indicating that n is not prime. And now, if none of the divisors evenly divide n, we return true, indicating that n is prime. And in the main function, we prompt the user to enter a number, and then we call the isPrime function to determine if the entered number is prime or not and print the result accordingly. Now let's discuss about function declaration. So in C, it's not mandatory for the definition of a function to precede its calls within the code. So suppose we have the average.c program, which contains the definition of the main function and the average function. Now let's imagine that we rearrange the code by placing the definition of the average function after the definition of the main function. And this reordering of code does not impact the functionality of the program. So even though the average function is defined after the main function can still call the average function without any issues. And this flexibility in the positioning of function definitions allow programmers to organize their code in a way that makes logical sense and enhances readability. And it enables the separation of concerns by grouping related functions together, regardless of their order in the code. However, it's essential to ensure that the function prototypes or declarations are provided before their first use in the code. And function prototypes inform the compiler about the existence and signature of functions, enabling proper compilation and linking of the program. And now let's see the code to demonstrate our previous slide. So here, the average function is defined after the main functions, and despite this arrangement, the main function can still call the average function without any issues, and the compiler is able to recognize the function prototype, also known as the function declarations, provided by the function's signature before its actual definition. And understanding that function declarations are not strictly required to precede their calls allows for more flexibility in organizing the code. However, it's still a good practice to provide function prototypes before their first usage, like I said before. And so when the compiler encounters the first call of a function before seeing its actual definitions, it lacks information about the function's return type and parameters. So in such cases, instead of producing an error message, the compiler makes an assumption to continue compiling the code. So let's illustrate this concept using our previous example. So in this example, when the compilers encounters the first call of the average function in the main function, it has no prior information about the average function's return type and parameters. So instead of halting the compilation process with an error, the compiler assumes that a default return type of integer for the average functions. And this assumption by the compiler is known as implicit declarations of the functions. However, relying on implicit declarations is not recommended as it can lead to unexpected behavior or any potential bugs in the program. And to avoid implicit declarations and ensure proper compilations, it's advisable to provide explicit function prototypes before their first usage. And this practice informs the compiler about the function's return type and parameters, facilitating accurate compilation. And so when the compiler encounters a function call before seeing its actual definition, it faces limitations in checking the correctness of the call. So consider our previous example where the average function is called in the main function before its definition. And when the compiler encounters the first call of the average function in the main function, it cannot verify whether we are passing the correct number of arguments or if the arguments have the appropriate types. So instead, the compiler performs default argument promotions and proceeds with compilations. However, when it later encounters the definition of the average function, it realizes that the function's return type is actually double, not integer. And as a result, the compiler generates an error message indicating a type mismatch. And this highlights the importance of providing explicit function declarations for their usage. And by declaring functions beforehand, the compiler could gain knowledge about the function's return type and parameters, enabling it to perform proper type checking and argument validations during compilation. And now, one way to address call before definitions by organizing our code in such a way that the definition of each function comes before any calls to that function. And this ensures that the program knows what each function does before it tries to use it. And however, it's not always possible or practical to arrange our code in this manner. Sometimes, due to the complexity of the program or the nature of the functions themselves, it's simply not feasible to define them all before any calls are made. And furthermore, even if we could organize our code in this way, it might actually make the program more difficult to understand. And putting function definition in an unnatural order can make it harder for developers to follow the flow of the program and understand its logic. So, while organizing function declarations before their calls can help avoid certain problems, it's not always the best solution and must be balanced with the consideration of code readability and maintainability. Fortunately, in C, there's a more practical approach to handle the issue of using functions before defining them by declaring each function before calling it. A function declaration serves as a preview for the compiler, giving it a brief overview of a function where full definition will come later in the code. And the general structure of a function declarations look like the one in the slide. Return type, function name, and parameters inside parentheses. And it includes the return type, name of the function, and any parameters it accepts within parentheses. And importantly, the declaration of a function must match its definition in terms of their return type, name, and their parameters. And this ensures consistency and prevents errors when the compiler tries to understand how the function works. And by using function declarations, we can effectively tell the compiler what to expect, making the code more organized and easier to understand. And here's a snippet of code demonstrating function declarations and definitions. Here, we first declare the average function before the main function. This declaration tells the compiler that there's a function named average, which takes two double arguments and returns a double. And then in the main function, we call the average function 3 times to calculate the average of different pairs of numbers. And finally, after the main function, we provide the definition of the average function. And this is where we tell the compiler exactly what the average function does. So it takes the numbers, adds them together, and divides the sum by 2 to get the average. And by separating the declaration and definition of the average function, we could ensure that the compiler knows what to expect when it encounters the function calls in the main function. And this helps in avoiding errors and making our code more organized and readable. So the type of function declaration we've been discussing is commonly referred to as the function prototypes. So they serve as a previews of functions that will be defined later in the code. And there's another style of function declaration in C which is older and less commonly used today. And in this style, the parentheses are left empty. And we can see the example of this declaration in orange colored code in the slide. And in this declaration, we don't specify the names of the function's parameters. We only provide their types, and this is acceptable in C, but it's generally considered best practice to include parameter names for clarity and readability. So while you can write function prototypes without parameter names, it's usually better to include them to make your code more easier to understand. So starting from the C99 standard, there's a rule that either a declaration or definition of a function must appear before any call to that function. So this means that before we use a function in our code, the compiler must have some information about it. And if we try to call a function without providing this information beforehand, it's considered an error by the compiler. So essentially, the compiler needs to know what the function looks like, its return type, their name, and parameters before the program can correctly process any calls to the function. So it's important to ensure that all functions are either declared or defined before they're used in the program to avoid compilation errors. And next, let's talk about arguments. So in C programming, when we pass arguments to a function, they're passed by value. This means that when a function is called, each argument is evaluated, and its value is assigned to the corresponding parameter within the functions. However, it's important to understand that when a parameter receives an argument's value, it's actually receiving a copy of that value, not the original value itself. And this distinction is crucial because any changes made to the parameter within the function do not affect the original argument outside of the function. So in other words, modification made to parameters inside a function do not reflect back to the argument passed to the function. And this behavior helps in maintaining data integrity and preventing unintended side effects in our programs. So here, the fact that arguments are passed by value offer both advantages and disadvantages. One significant advantage is that since parameters receive copies of our argument values, we can manipulate these parameters within a function without altering the original arguments, and this allows us to treat parameters as variables within the function, which can help reduce the number of distinct variables needed in our code. And by utilizing parameters as variables, we can streamline our code and make it more concise and organized. And this can lead to more clear and more efficient programs as we can perform necessary operation within the function without cluttering our code with unnecessary variables. Now let's take a look at a function that illustrates how arguments are used in C programming. And this function is designed to raise a number x to a power n. In this function named power, two arguments are passed, the x and n, both of type integer, and the function calculates the result of raising x to the power of n using a loop. And the for loop iterates from 1 to n, multiplying result by x in each iteration, and finally the function returns the calculated result. And this function serves as an example of how arguments are utilized within a function to perform specific tasks. And the values passed as arguments influence the behavior and outcome of the function, demonstrating the practical use of arguments in C programming. Now, let's delve deeper into the function we discussed earlier, which raises a number x to a power n. And we'll consider a modification to the function that demonstrates an important concept regarding arguments in C programming. So in this modified version of the function, the parameter n is used directly within the loop without the need for an additional variable like I. And this is because n is a copy of the original exponent passed to the function. And the while loop iterates n times, decrementing n with each iteration until it reaches 0. And inside the loop, result is multiplied by x for each iteration, effectively calculating x n. And by directly using the copy of the original exponent n, the function simplifies its logic and removes the need for an extra variable. And this shows a case how arguments being passed by value can be utilized efficiently within functions in C programming. C language's requirement that arguments be passed by value presents challenges when writing certain types of functions. So let's consider a specific example to illustrate this point. Suppose we need to create a function that decomposes a double value into its integer and fractional parts. And this task might seem straightforward, but due to the nature of how arguments are passed in C, it becomes a bit more complex. So in this scenario, we want to extract both the integer part and the fractional part from a double value. But however, because the arguments are passed by value, any modification made to the parameters within the function will not affect the original arguments outside of the function. So this means that directly manipulating the double value within the function separate its integer and fractional parts become challenging. We cannot simply modify the original value passed to the function to achieve this decomposition. So while C's pass by value approach offers simplicity and efficiency in many cases, it can pose challenges when dealing with certain types of functions that require direct manipulation of arguments. And in situations where we need a function to perform a task like decomposing a double value into its integer and fractional parts, we encounter a challenge. A function in C cannot directly return multiple values. So one approach to tackle this challenge is by passing variables to the function and having it modify them to store the desired values. Now let's consider the orange colored function here in the slide. So in this function we pass three variables, the double value x, and two variables, integer part and fractional part, to store the integer and fractional parts respectively. And inside the function, the integer part is extracted from x and stored in integer part. And the fractional part is then calculated by subtracting the integer part from x, and the result is stored in the fractional part. However, there is a critical issue with this function. Since arguments are passed by value in C, any modifications made to the parameters integer part and fractional part within the function will not reflect outside of the function. Therefore, this approach doesn't achieve the desired outcome of decomposing double value into its integer and fractional parts. So we need to explore alternative strategies to overcome this limitation of C functions. And now let's examine how the function we discussed earlier, decompose, is called and why it doesn't achieve the desired outcome. Here we have the function called decompose. In this call, we're passing double value pi as the first argument and the two variables I and d as the second and third arguments respectively. And the intention is for the function to modify I to store the integer part of the pi and d to store its fractional part. However, due to how arguments are passed by value in C, the modifications made into integer part and fractional part within the function will not reflect outside of the function. So as a result, after the function call, int will not be affected by the assignments made within the decompose function. And to address this issue and ensure all decompose work correctly, we need to explore techniques outlined in chapter 11 of the course materials later. And these techniques will enable us to achieve the desired behavior of decomposing a double value into its integer and fractional parts effectively within a function. And next, in C programming, we have the flexibility to make function calls even when the types of the arguments don't exactly match the types of the parameters declared in the function. Now, how these arguments are converted into the types expected by the parameters depends on whether the compiler has a prototype for a function or the full definition of the functions before the call. So, if the compiler has already seen a prototype for a function, or if it has the full definition of function available, it can apply certain rules to convert the arguments appropriately to match the parameter types. So, these rules ensure that the function can be called with arguments of different types, providing flexibility and convenience in our programming. However, it's also essential to understand these conversion rules to ensure the correct behavior of our programs. Now, let's see these rules in details on our next slide. First, when the compiler has encountered a prototype of a function before a call, it performs certain conversions to ensure that the types of the arguments match the types of the parameters expected by the function. So, in this scenario, the value of each argument is implicitly converted to the type of the corresponding parameter as if by assignment. So, for example, if we pass an integer argument to a function that expects a double, the argument will be automatically converted to a double before being passed to the function. And this conversion ensures that the function receives the correct type of data it expects, even if the argument provided initially has a different type. And this implicit conversion mechanism allows for smoother interactions between different data types and function calls, enhancing the flexibility and usability of functions in C programming. And secondly, when the compiler has not encountered a prototype of a function prior to a call, it will perform default argument promotions to ensure compatibility between the arguments and parameters. One aspect of default argument promotion is that float arguments are automatically converted to double. This means that if we pass a float to a function that expects a double, the float will be promoted to a double before being passed to the function. And additionally, integral promotions are performed, which involves converting character and short arguments into integer. In C99, this process is refined and it's known as integer promotions. This means that character and short arguments are automatically converted to integer before being passed to the function. And this default argument promotion ensures that the function receives arguments of compatible types, even if they were originally of different types. And this will help maintain the consistency and the correctness in our code, especially when dealing with functions that have not been prototyped before their calls. However, relying solely on default argument promotions can lead to unexpected results and potential errors in our programs. Now let's illustrate it with this example here. So in this code we have here in the slide, we have a main function that declares a variable x of type double and assigns it the value of 3.0. And then we attempt to call a function named square with x as its argument. The square function, however, expects an argument of type integer, and since we haven't provided a prototype for a square function before calling it, the default argument promotions come into play. And in this case, the double value of x is promoted to an integer when passed to the square function. And as a result, the square function receives 3 instead of 3.0. And this leads to unexpected behavior when the printf function attempts to interpret the result of square x as an integer and prints it using the deformat specifier. And to avoid such issues, it's crucial to provide function prototypes before calling functions, especially when dealing with different arguments type. This ensures that the compiler can perform the necessary conversions correctly and prevent potential errors in our code. And when we call the square function in the previous example, the compiler doesn't yet know what type of argument the square function expects, and this lack of information about the function's parameters led to potential issues with argument conversions. And since there's no prototype provided for a square function before it's called, the compiler doesn't have any information about the function's parameters. And as a result, it defaults to a process called default argument promotions when processing the argument provided to square. And in this case, the double value x is promoted to an integer because the square function is not explicitly declared to expect a double. And this default promotion causes the printf functions to interpret the result of square as an integer, leading to unexpected behavior when printing the result. And to avoid such problems, it's essential to provide function prototypes before calling functions, especially when dealing with different argument types, and this will allow the compiler to correctly interpret the types of arguments passed to functions and perform appropriate conversions as needed, ensuring the proper functioning of our program. In the case where the square function is called without a prototype, the compiler resorts to a default argument promotions. However, because it is not aware of the specific type expected by the square, it performs these promotions on the argument provided to the functions. And in the previous example, the variable x is of type double. But when we pass it to the square, it undergoes default argument promotions, which attempt to convert it to an integer. However, this conversion doesn't have any effect on x itself. And as a result, when square is called with x, it receives a double argument instead of the expected integer. And this discrepancy leads to undefined behavior, meaning the The result of the function call cannot be predicted, and to resolve this issue, ensure that the square receives the correct type of argument, and we can explicitly cast x to an integer before passing it to square, and this casting operation informs the compiler to treat x as an integer when calling square, thus avoiding any ambiguity or undefined behavior. And therefore, the corrected function call will be the one at bottom of our solid. And by explicitly casting the argument to the correct type, we ensure that the square receives the expected type of data, promoting clarity and reliability in our code. A more effective solution to prevent issues with argument conversions, such as the one we encountered when we calling the square function, is to provide a prototype for a function before calling it. And in C programming, a function prototype serves as a declaration of the function's signature, specifying its return type and parameter types. And by including a prototype for a square before its invocation, we inform the compiler about the function's expected parameters, allowing it to perform proper argument conversions. So in modern C standards like C99, calling a function without first providing a declaration or definition for it is considered an error, and this rule ensures that all functions are properly declared or defined before their use, helping to prevent potential issues with argument conversions and any other errors in our programs. And when a function parameter in C is a one-dimensional array, it's possible to leave the length of the array unspecified in the parameter declaration. So, for example, we have our code snippet here in this slide. In this case, the function f expects an array A as its parameter, but it doesn't specify the length of the array explicitly. And this allows us to pass arrays of different lengths to the function f. However, it's important to note that C does provide an easy way for a function to determine the length of an array passed with. Unlike some other programming languages, C does not inherently track the length of arrays. Therefore, if the function is to know the length of the array it receives as an argument, we'll have to supply the length as an additional argument to the function, and this will ensures that the function has the necessary information to process the array correctly and to promote clarity and reliability in our code. And now let's see the example that demonstrates how to work with array arguments and functions. So consider the following function SUMArray, which calculates the sum of all elements in an array. And in this function, array A represents the array of integers, and n specify the length of the array. And the function iterates over each element of the array, adding its value to the sum variable. And since the SUMArray function needs to know the length of the array A, in order to loop through all its elements, we must provide this length as the second argument when we call the function. So for example, to calculate the sum of elements in an array, or length, we will call SUMArray length as an argument, and by supplying the length of the array as an additional argument, we ensure that the SUMArray function has the necessary information to process the array correctly, and it will enable us to perform operations on arrays within functions effectively. And the prototype for the SUMArray function, which we discussed in the previous slide, typically looks like this. The first code in the slide. So in this prototype, the integer array A represents the array parameter, and integer n specified the length of the array. However, it's worth noting that we can omit the parameter names if we wish, resulting in a prototype like the one at the bottom of the slide. In this simplified version, we do not specify the names of the parameters, and this can be useful in situations where the parameter names are not important or when we are only interested in declaring the types of the parameters. And both versions of the prototype convey the same information to the compiler about the function SUMArray, specifying the types of its parameters and their return values. And this helps to ensure consistency and clarity in our code, and it will promote better understanding and maintainability for our program. And when we call the SUMArray function, we provide two arguments. First is the name of an array and its length. So, for example, if we have an array named numbers and we want to calculate the sum of its elements, we will call SUMArray with numbers and length as the arguments respectively, where numbers is the name of the array and length is the number of elements in the array. And in this call, the first argument numbers is the name of the array itself. So when passed to the function, it behaves like a pointer to the first element of the array. And second argument length specifies the number of elements in the array. And this information is crucial for SUMArray function to know how many elements to iterate over in order to calculate the sum accurately. And by providing both the array name and its length as arguments, we enable the SUMArray function to access and process the elements of the array correctly and accurately. And in C programming, when we pass an array to a function, we do not include brackets after the array name. So let's examine an example to understand this concept better. So here in the slide, we have a code snippet colored in blue. In this example, we have an array named B with a length defined by the constant len or len. We want to calculate the sum of the elements in this array using a function called SUMArray. And when we call the SUMArray function, we pass the array B as the first argument and len as the second argument. However, notice that we do not include brackets after the array name B when we're passing it to the function. The correct way to pass the array to the function is SUMArray B len without the brackets, and including brackets after the array name as shown at the bottom of the slide is incorrect. This incorrect syntax may lead to compilation errors or unexpected behavior in our programs. And by understanding this convention of passing arrays to functions without brackets, we ensure that our code is written correctly and functions as intended. And now in C programming, it's important to understand that a function has no built-in mechanism to verify whether we've passed it the correct length of an array. And this lack of validation can be exploited in certain situations. For example, you can tell a function that an array is smaller than it actually is, allowing us to manipulate only a portion of the array. Let's see this with an example. So suppose we have an array named B that can hold 100 numbers, but we've only stored 15 numbers in it. We can then call the SUMArray function and specify that we want to sum only the first 50 elements of the array, like the example in our slide. And this call, B is the name of the array and 50 indicates the number of elements we want to sum. And by passing a smaller number as the length of the array to the function, we effectively manipulate only the specified portion of the array. And this technique allows us to perform operations on arrays more flexibly depending on our specific requirements. However, it's important to use it judiciously and ensure that our code remain clear and understandable to others who may read it. And when working with an array arguments and C functions, it's crucial to exercise caution and ensure that we provide the correct length of the array to avoid potential issues. So for example, if we mistakenly tell a function that an array argument is larger than it actually is, we risk encountering undefined behavior. Let's see this in a scenario. So in this scenario, we have a total equal to some array with b and 150 as the argument. And this call, b is the name of the array and 150 indicates the number of elements we want to include in the sum. However, if the actual size of the array b is smaller than 150, the SUMARray function will attempt to access elements beyond the end of the array. And this action leads to undefined behavior, meaning the result of the function call can't be reliably predicted, and it may cause errors, crashes, or produce unexpected results. And therefore, it's imperative to ensure that the length specified when passing an array to a function accurately reflects the actual size of the array. And this helps prevent issues such as accessing out-of-bounds memory and promotes the robustness and reliability of our code. And now in C programming, a function can modify the elements of an array parameter, and its modifications are reflected in the corresponding argument. And now let's explore an example to illustrate this concept. So consider a function called store zeros here in our slide that modifies an array by storing 0 into each of its elements. So in this function, array A represents the array parameter, and the n variable specifies the length of the array, and the function iterates over each element of the array using a loop and assigns the value 0 to each element. And when we call the store zeros function with an array argument such as store zeros with array and length as an argument respectively, the elements of the array are modified and each element is set to 0. And after the function call, the changes made to the array within the functions are reflected in the original array passed as an argument. And this means that the array will now contain all zeros in place of its original elements. And this behavior demonstrates how functions in C can directly manipulate array elements, and providing a powerful mechanism for performing various operations on arrays within functions. And when we call the store zeros function, such as store zeros with b as the first argument and 100 as the second argument, the function modifies the elements of the array b by setting each element to 0. And this ability to modify array elements within a function may seem contradictory to the fact that C passes arguments by value. However, it's essential to understand that although C passes arguments by value, when we pass an array to a function, we're actually passing a pointer to the first element of the array. And this pointer allows the function to access and modify the original array directly, rather than creating a copy of the entire array. The chapter 12 of your textbook will delve deeper into this concept and will explain why there's no contradiction between passing arguments by value and the ability to modify array elements within functions. And by understanding how array arguments are passed and manipulated in C, you'll gain more understanding of how functions interact with arrays and how to utilize this feature in your program. And when dealing with multi-dimensional arrays as function parameters in C, it's important to note that only the length of the first dimension may be omitted. Now, let's explore this concept further. So, for example, if we revise the sum array function to accept a two-dimensional array, we must specify the number of columns in the array. This is because the compiler needs this information to correctly interpret the array elements. Here we have the modified sum two-dimensional array that of course operates on a two-dimensional array. So in this function we must specify the number of columns in the array, while the length of the first dimension can be left unspecified. So in this example, the array A with the first row and with the row unspecified and the column len will represent the two-dimensional array parameter, where the number of rows n must be specified, but the number of columns len is left implicit. So when we pass a two-dimensional array to this function, we only need to specify the number of rows, and the compiler already knows the number of columns because it's specified in the function parameter. And the function then iterates over each element of the two-dimensional array using nested loop, calculating the sum of all elements. And working with multi-dimensional arrays in C can sometimes be challenging. So, because particularly when trying to pass arrays with an arbitrary number of columns as function arguments. So one workaround for this limitation involves using arrays of pointers as explained in chapter 11 of your textbook. So by using arrays of pointers, we can effectively work with multi-dimensional data structures, allowing for more flexibility and versatility in our programs. But however, C99 introduces another solution that offers even greater convenience: variable length array parameters. With variable length array parameters, we can pass multi-dimensional arrays to functions without needing to specify the number of columns explicitly, and this feature will simplify the process of working with multi-dimensional arrays. And in C99, like I've said before, a new feature called variable length array parameters allows us to define functions with parameters that are variable length arrays. So for example, here we can see the code in orange in our slide. In this function, array A is a parameter representing an array, and n is another parameter representing the length of the array. However, it's important to note that there is no direct link between n and the actual length of the array A. Although the function treats n as the length of the array, the actual length of the array may be larger or is smaller than n, and this means that we must be cautious when using n to iterate over array or perform operations involving array elements. So in C99, the variable length array parameters provides a way to explicitly specify the length of an array within a function's parameter list. So now let's see the example we have here in the slide. So this function definition, n is the first parameter representing the length of the array A, and the second parameter A square bracket n declares an array with the length specified by the value of n. And it's important to note that the order of the parameters is crucial when using variable length array parameters. So here's the first parameter n specifies the length of the second parameter a. Therefore, the order of the parameters must be maintained to ensure correct interpretation of the array length. And by using the variable length array parameters in this manner, we can clearly and explicitly indicate the length of the array within the function's signature. And when writing a prototype for a function with variable length array parameters in C99, there are different approaches we can take to declare the array parameter. So let's explore two common possibilities. First one, we can write the prototype to mirror the function definition exactly, specifying the array length within square brackets, like the first code snippet we have here in this slide. So in this version, the array parameter a is declared with a length specified by the value of n, just like in the function definition. And second one, alternatively, we can replace the array length with an asterisk, indicating that the length of the array is variable, like the red code we have here at the bottom of our slide. So here the asterisk signifies that the array A has a variable length determined by the value of n, and both of these versions are valid ways to declare a function prototype for a function with variable length array parameters, and the choice between them may depend on personal preference or coding style conventions. And regardless of the chosen version, the function prototype ensures that the function is correctly declared and can be used effectively in the program. And now in C99, when declaring a function prototype with variable length array parameters, we have different ways to represent the array length. One of these methods involves using an asterisk, like I've said before, instead of specifying the array length directly. So, for instance, consider the following function prototype at the bottom of this slide. In this version, the parameter name for the array is omitted, and the array length is denoted by an asterisk. This notation serves as a clue that the length of the array is related to parameters earlier in the parameter list. And the reason for using the asterisk notation is that parameter names are optional in function declarations. So if we were to omit the parameter name and use square brackets to specify the array length directly, it wouldn't be clear how the length of the array is determined. And by using the asterisk notation, we provide a clear indication that the array length is variable and related to earlier parameters in the parameter list. And in C99, when declaring a function prototype with variable length array parameters, we can also leave the brackets empty, as we typically do when declaring an array parameter. Now, let's explore the two versions of this notation. So first, we can leave the brackets empty, providing the array parameter with a name like the version 3a here. Or alternatively, we can omit the parameter name and leave the brackets empty, like the version 3b here. While both versions are legal, leaving the brackets empty may not be the best choice because it doesn't clearly expose the relationship between the parameter n and the array a, unlike the previous versions where the asterisk or the array size notation provided a hint about the array's length being variable. Empty brackets may obscure this relationship. So it's recommended to use one of the previous versions that explicitly indicate the variable length nature of the array parameter. This will improve the clarity of your code and understanding of the function prototype. So next in C99, the length of a variable length array parameter is not limited to a constant value. It can be an expression. So let's consider a function concatenate that concatenates two arrays A and B, storing the result into a third array C. So in the function we have in the slide here, the length of the arrays A and B are specified by the parameters m and n respectively, and the length of the resulting array C is determined by the expression m plus n, representing the total numbers of elements in a concatenated array. And by allowing expressions to define the length of variable length array parameters, we gain flexibility in function definitions, and this will enables us to work with arrays of varying lengths and making our code more adaptable to different scenarios and data sizes. And in C99, when specifying the length of a variable length array parameter, the expression used can involve not only other parameters within the function, but also variables outside the functions or even calls to other functions. So for example, in the concatenate function we discussed earlier, the expression m plus n used to determine the length of array C involves the parameters m and n. However, it's important to note that this expression could also involve other variables declared outside the function, like for example, global variables, or even call to other functions to compute the array length dynamically. And so, variable length array parameters with a single dimension offer some benefits, but they also come with limitations. So firstly, they enhance the descriptive quality of function declarations or definitions by explicitly stating the desired length of an array argument, and this clarity can make the functions more understandable and easier to use. However, it's important to note that variable length array parameters do not provide additional error checking capabilities. Despite specifying the desired length, it's still possible for an array argument to be either too long or too short. So, in other words, while variable length array parameters improve readability and expressiveness, they do not inherently prevent runtime errors caused by inappropriate array length. So, it's essential for the programmers to ensure that the array lengths are properly validated and it's properly managed within the function implementation to avoid any potential issue during the runtime. And variable length array parameters become particularly useful when dealing with multi-dimensional arrays. So consider the function sum two-dimensional array, which we discussed earlier. So instead of fixing the number of columns to a specific value like macros len, we can use a variable length array parameter to generalize the function to handle arrays with any number of columns. Now let's see the function sum two-dimensional array here. So this function calculates the sum of elements in a two-dimensional array with dimensions n rows and m columns. And by using a variable length array parameter a and m, the function can be applied to arrays of different sizes, providing greater flexibility and reusability. And variable length array parameters allows us to generalize functions like sum two-dimensional array to handle arrays with any number of rows and columns. And This versatility simplifies code maintenance and promotes code reuse, making our programs more adaptable to varying data structures and requirements. And the function sum two-dimensional array can be prototyped in several ways to accommodate a variable length arrays in C99. And here in the slide we can see some examples of prototypes for this function. The first code shows how to specify the array dimension directly, and in second code we can use asterisks to represent unspecified dimensions, and next we can also omit the first dimension in the third code, and lastly omitting the second dimension in the last code. And each prototype specifies the same function, sum two-dimensional arrays, but they vary in their representation of the array dimensions. And the choice of which prototype to use depends on the desired level of abstractions and flexibility needed. And now in C99, the keyword static can be used in array parameter declarations to indicate certain guarantees about the array's length. Now, consider the example we have in the slide here. So in this declarations, static 3 indicates that the array A is guaranteed to have a length of at least 3 elements. So this means that the function sum array expects an array A with a minimum length of 3 elements. And using static in this context provides additional information to the compiler and potentially allows for optimization or additional error checking at compile time. So the keyword static, like I've explained before, can be utilized in array parameter declarations, but its presence doesn't directly impact the behavior of the program. And when static is used in an array parameter declarations, it serves as a hint to the compiler. And while it doesn't alter the program's functionality, it may assist the compiler in optimizing the code by generating more efficient instructions for accessing the array. And it's essential to note that the use of static in array parameter declaration is restricted to the first dimension only when we're dealing with multi-dimensional arrays. So in other words, you cannot use static for subsequent dimensions beyond the first dimension. And now let's return to our initial sum array function. So typically when sum array is invoked, the first argument provided is the name of an array. So for instance, we have our integer array b here and the total variable that takes value from sum array function. Here b represents an array that is declared as a variable and initialized before being passed to sum array. However, if b isn't required for any other operation and is solely intended for use within the sum array function, creating this one seems unnecessary. So in such cases, instead of creating a separate array variable like b, you can directly pass a list of values to sum array. And this is where static and array parameter declarations come into play. So by utilizing static in the array parameter declaration of sum array, you can directly pass a list of values to the function without the need to create an array variable beforehand. So to overcome this inconvenience in C99, we can utilize a concept called a compound literal. So it's essentially an unnamed array that's generated dynamically, and it allows us to specify its elements directly within the function call itself. Now let's see the invocation of sum array with a compound literal as its first argument here in our slide. So here the bold code represents a compound literal, and it denotes an array containing specific elements, which is 3, 0, 3, 4, 1. And by using this approach, we can pass the array elements directly to the SumArray function without the need to create a separate array variable beforehand. And in this scenario, we didn't explicitly specify the length of the array within the compound literal. Instead, its length is automatically determined based on the number of elements provided within the literal. However, we also have the flexibility to explicitly define the length if needed. So, for instance, our first code example here in the slide and the second code here are equivalent expressions. So, both representing an array with 4 elements, the 1, 9, 2, and 1. And this feature of compound literals offers versatility and convenience. And this will allows us to create arrays with specific lengths directly within function calls or assignments. And a compound literal in C, like the integer array size 10 with the first value 8 and 6, behaves similarly to a cast applied to an initializer. So essentially, compound literals and initializers follow the same set of rules, much like designated initializers. So a compound literal can include designators. And moreover, it's possible for a compound literal to lack full initialization. So in such cases, any uninitialized elements are automatically set to 0. So for instance, consider the example here in the bottom of the slide. It consists of 10 elements. The integers consist of 10 elements, and the first 2 elements are explicitly initialized to 8 and 6 respectively, while the remaining elements are implicitly initialized to 0. And so compound literals in C99 offers flexibility beyond just constants. They can incorporate arbitrary expressions, as demonstrated in the example here in this slide. So here, the total is assigned the result of a SumArray, where the first argument is a compound literal containing expressions like 2 multiplied by I plus j, and j multiplied by k. And furthermore, compound literals are elf values, meaning their elements can be modified if necessary. However, if immutability is desired, you can designate the compound literal as read-only by appending const to its type, like the one in the bottom of this slide. And this expression creates a read-only compound literal with elements 5 and 4. And in C, when you create a function that is not meant to return nothing, which is also known as a non-void functions, you can use something called the return statement to tell the function what value it should give back. So the return statement looks like this, like the first code that we have in the slide. Now, what is this expression? Well, it's what the function will calculate and hand back to whoever called it. And the expression can be pretty straightforward. It might just be a number or a variable holding a value. So for instance, you might see something like return 0 or return status, but C also allows us to get a bit fancier. We can use more complex expressions too. So here we have the ternary conditional operator. So we can use it here like the code at the bottom of our slide. So what actually is happening here? So if n is greater than or equal to 0, we return n. Otherwise, we return 0. So in short, the return statement is like the delivery guy of a function. It makes sure that Whatever your function's job is, it hands back the right answer. Now let's delve deeper into the return statement in C programming. Now, here's an important rule to keep in mind. So when you use a return statement, the type of the expression you're returning should match the function's return type. But what will happen if they don't match? Well, C is a bit smart about it, so it will perform something called implicit conversion. So implicit conversions, like we've covered on our previous slides, on our previous videos, is like a behind the scenes adjustment to make things work smoothly. So here's an example. Say your function is supposed to give back an integer, but your return statement has a double expression. And in this case, C will convert that double expressions into an integer before returning it. So it's like translating between two languages to make sure everyone understands each other. And now let's continue our exploration of the return statement in C programming. So here's an interesting aspect. So return statements can also be used in functions whose return type is void. So when you're using return in a void function, you do not need to provide any expressions after it. So for instance, take a look at the example we have in our slide here. So in this code snippet, we have a function called print integer that takes an integer I as an argument, and if I is less than 0, the function just returns without doing anything else. But if I is greater than or equal to 0, it goes ahead and prints I. And so even in void functions, return statements have their place. They can serve as an exit point, signaling the end of the function's job without necessarily returning any specific value. Now, continuing our discussion on return statement, let's explore a couple more scenarios. So first off, even in a void function, you might spot a return statement at the end. So it's like a little extra reassurance, though it's not entirely necessary. And take the function we have in our slide here. For example, here, the print pun is a void function that simply prints out a pun. So after printing, it politely says return, even though it doesn't need to do, because the function is already at its end. It's like saying I'm finished, but just to make it sure, I'm officially ending it here. Now, in a non-void function, if you forgot to include a return statement, things could get messy. So the program will not know what to do if it tries to use the function's return value. So it's like having a phone call where one person never says goodbye and it leaves everyone hanging and unsure of what's supposed to happen next. So remember to always have a return statement in your non-void functions. And now let's shift our focus to program terminations. So typically in C programming, the return type of the main function is specified as integer, and this integer before main tells the program that when it's done running, it will send back an integer value to whoever called it. And by convention, returning 0 usually means everything went smoothly, while other values might indicate errors or specific conditions. However, in older C programs, you might come across a simpler version of main, like the code snippet at the bottom of our slide. In these older programs, the return type for main is often left out altogether. Why? Well, C is flexible and it used to assume that if you didn't specify a return type for main, it defaulted to integer. So it's like an agreement between the programmer and the language. But please remember, while this older style might still work, it's considered a bit outdated, and Modern programming practices encourage explicitly stating the return type for main. And now let's discuss a bit more about program termination in C programming. So, firstly, it's important to note that in modern C programming, omitting the return type of a function, including main, is not allowed according to the C99 standard. This means it's considered a violation of the language rules. So, therefore, it's advisable to steer clear of this practice to ensure compatibility and compliance with current standards. And furthermore, although it's still technically legal to omit the word void in the parameter list of the main function, it's generally recommended to include it. And this parameter list specifies that the main function doesn't take any arguments, including void explicitly communicates this fact, making the code clearer and easier to understand for other programmers who might read it later on. And now, like I've said before, when a C program reaches its end and terminates, the values returned by the main function serves as a status code. And this status code can be examined by the operating system or other programs that call the C program. And in the case of normal termination, it's customary for a main function to return 0. And this indicates to the operating system that everything went smoothly and the program executed as expected. However, in situation where the program terminates abnormally, perhaps due to an error or exceptional condition, it's recommended for the main function to return a value other than 0. And this non-zero value serves as a signal to indicate that something unexpected occurred during the program execution. So, in a sense, it's considered good practice to ensure that every C program returns a status code upon termination. And now let's explore another method of terminating a program in C by using the exit function. So we've learned that using a return statement in the main function is one way to end a program. However, there's an alternative approach available, that is by using the exit function. This function is a part of the start library and can be found in the start library header file. And similar to the return value of the main function, the argument passed to the exit function also signifies the program status at the time of termination. So in essence, both serve as indicators of how the program concluded its execution. So for instance, to signify normal termination, we can pass the value 0 to the exit function, like the example at the bottom of our slide here. And this tells the operating system that the program completed its task successfully without encountering any issues. And in our previous slide, we saw that passing 0 to the exit function signifies normal termination. However, to make our code more readable and expressive, C provides us with two predefined macros for this purpose. So the first macro is exit success, and using this macro in place of 0 has this XXM effect, but it makes our intention clear to anyone reading the code. And conversely, if the program encounters an abnormal termination condition, we can use the macro exit failure. Both exit success and exit failure are defined as macros in the start library header file, and the actual values of these macros may vary depending on the implementation, but commonly exit success is assigned the value 0 while exit failure is assigned the value 1. And by using these macros, we enhance the clarity and portability of our code, making it easier to understand and maintain. And now let's further explore the exit function in C and understand its relationship with the return statement in the main function. So when we use the statement return expression in the main function, it's essentially equivalent to calling exit expression. And both of these statements signal the end of the program execution and return a value to the operating system. However, there is an important distinction between using return and exit. The exit function causes a program to terminate unconditionally, regardless of which function invokes it. In contrast, the return statement in the main function only leads to program termination when it's executed within main itself. So imagine the program as a series of rooms with each function call being a door leading to another room. When the exit function is called, it's like triggering a fire alarm that forces everyone to leave the building immediately, regardless of where they are. On the other hand, when the return statement is encountered in the main function, it's like reaching the end of a guided tour and signaling the participants to exit the building in an orderly manner. And now let's explore the concept of recursion in programming, particularly within the context of the C programming language. So recursion occurs when a function calls itself. So it's like looking into a mirror and seeing reflections within reflections, and the function repeats itself each time, addressing smaller part of the problem until it reaches a base case. Here in this slide, we can see an example of a recursive function that computes the factorial of a number, denoted as n factorial. As a function, we have a base case. If n is less than or equal to 1, we return 1, and this serves as the stopping condition for the recursion. Otherwise, we recursively call the fact function with argument n negative 1 and multiply the result by n. And the process continues until we reach the base case. And recursion can be a powerful tool in programming, allowing us to solve complex problems by breaking them down into smaller, more manageable pieces. However, it's essential to ensure that the recursive function has a base case and converges towards it to avoid infinite recursion. And now let's take a closer look at recursion and understand how it works by tracing the execution of a specific statement. And now suppose we have the statement I equal to fact with the 3 as the argument, and this means we're calling the fact function with the argument 3 and assigning its result to the variable I. Now let's trace through the execution of this statement to see how recursion unfolds. So when we call fact3, the function checks if the argument 3 is less than or equal to 1. So since it's not, the function proceeds to call fact2. So similarly, inside fact2, the function checks if 2 is less than or equal to 1. Again, it's not, so the function calls fact1. Now, within fact1, the function finds that 1 is indeed less than or equal to 1, which satisfies the base case condition. Therefore, it returns 1. This return value of 1 then bubbles up through the previous function calls, and fact1 returns 1, and fact2 receives this return value of 1 and multiplies it by 2, resulting in 2. So fact2 returns 2. And finally, fact3 receives the return value of 2 from fact2 and multiplies it by 3, yielding 6. And thus, the factorial of 3 returns 6. So in essence, each recursive call to the factorial function works on a smaller part of the problem until it reaches the base case, at which point it starts returning values back up the chain. So this process will continue until the original function call is resolved, providing us with the final result. And now let's explore another example of recursion by examining a function that computes the value of x to the power of n, where x is a base number and n is the exponent. So here we have the recursive function for its problem in the slide. So in this function we have two parameters, x, which represents the base number, and n, which represents the exponent, and the function first checks if the exponent n is equal to 0. So if it is, it returns 1, and this one serves as the base case for the recursion. So if the exponent n is not 0, the function computes x to the power of n recursively. It does this by multiplying x with the result of x raised to the power of n subtracted by 1. Now let's walk through an example to see how this function works. Now suppose we call power with argument 2 and 3. First, the function checks if n is 0. And since n is not 0, we proceed to the else block. And next, we return x multiplied by power 2. It will have the argument 2 and 2. And inside power 2, we again check if n is 0. It's not, so we proceed to the else block. And we return x multiplied by power 2 and 1. And inside power 2 and 1, we once again check if n is 0, and it's not again, so we proceed to the else block, and we return x multiplied by power 2 and 0. Now, in power 2 and 0, the base case is satisfied, which is the n is 0, so we return 1. And then we start unwinding the recursive calls. Power 2 and 0 returns 1, power 2 and 1 returns 2, and powers 2 and 2 returns 4, and powers 2 and 3 returns 8. So power 2 to the power of 3 evaluates to 8. And this shows how recursion can be used to solve mathematical problems by breaking them down in smaller and more manageable subproblems. And now let's discuss more about recursion by exploring a more condensed version of the power function and discussing the importance of termination conditions in recursive functions. So here in the slide we can see a more concise implementation of the power function from our previous slides. So here in the slide we use a conditional expression, and we use this conditional expression to check if the exponent n is equal to 0, and if it is, we return 1, indicating the base case. Otherwise, we return x multiplied by the result of calling power recursively with x and -1 and n -1, and this condensed form of the function achieves the same result as the previous implementation, but in a more concise manner. And it's important to note that both the factorial and power function are careful to test a termination condition as soon as they called, and this termination condition is crucial in preventing infinite recursion. And all recursive functions require some form of termination condition to ensure that the recursion eventually stops, and without it, the functions will keep calling itself indefinitely, leading to what's known as infinite recursion, which can cause the program to crash or our computer run out of memory. And by including a termination condition, we ensure that the recursive process stops when it reaches a certain point, allowing the function to return a result and preventing any undesirable consequences. And I think that's all for the material. Here we have several exercises that you can do by your own. And if you have any problems or question regarding the exercises, you can reach out to me or Pak Wira for assistance. And now let's wrap up our discussion on functions in C programming, and let's recap the key points covered in this video. So firstly, incorporating functions into programs enhances their modularity. And by breaking down tasks into smaller, more manageable functions, we can organize our code more efficiently and make it easier to understand, maintain, and debug. And next, functions serve as a means of code reusability, allowing us to write a block of code once and then use it multiple times throughout our program. And this will help us to reduce redundancy and promotes cleaner, more concise code. Furthermore, functions can be classified as either iterative or recursive. Iterative functions use loops to repeat a block of code until a certain condition is met, while recursive functions call themselves to solve a problem by breaking it down into smaller subproblems. And when passing arguments to functions, we have two methods, by reference and by value. Passing by value involves passing a copy of the variable to the function, ensuring that the original variable remains unchanged. And on the other hand, passing by a reference allows the function to directly access and modify the original variable's memory address. And understanding these concepts is essential for writing effective and efficient C programs. And by leveraging functions and mastering their usage, programmers can create a well-structured, modular code that is easier to develop, maintain, and scale. So, in summary, functions play a pivotal role in C programming, enabling the code reusability, modularity, and efficient problem solving. And whether using iterative or recursive approaches, and whether passing arguments by reference or value, functions provide a powerful toolset for building robust and scalable software solutions. I think that's all from me. You can access the code and slide that I use in this video by clicking the link in this video description. I hope you all have a great time learning C programming, and see you later in the next video.